Hello everyone, this video is brought to you by the Atılım Üniversitesi OpenCourseWare project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and the video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem in Chapter 7. As you see in this figure, a box of mass 50 kilograms slides down the frictionless slope at constant speed with the help of a force F, which is applied parallel to the slope and pulls the box up. In this problem, we will find the magnitude of F in part A. Determining first all the forces acting on the box, we will calculate separately the work done by each force in part B. And finally, we will find the work done by the net force on the box. Okay, let's start. First, we write the given physical quantities in the SI units. Next, as always, we draw the free body diagram of the box. Here, mg is the gravitational force, n is the normal force, and F is the applied force on the object. Additionally, vector d denotes the displacement vector. To find the magnitude of F, we should first notice that in order for the box to move at constant speed, its acceleration along the slope must be zero. And by the Newton's second law, F is m times g times sine theta. From the figure, sine theta is nothing but h over d. As a final step, substitute the given quantities into the equation as 50 kilograms times 9.8 meters per second squared times 2 meters over 3.6 meters. Then force F is found to be approximately 272 newtons. And this is the answer to the question in part A. In part B, we calculate separately the work done by each force. Using the formal definition of work, we find the work done by the normal force as n dot d, which is the scalar product of two vectors, and the result is just a scalar, not a vector. Note that the angle between the normal force and the displacement vector d is 90 degrees. So the result is n times d times cosine 90 degrees. And since cosine 90 degrees is 0, then the work done by the normal force is just 0. The work done by force F is F dot d. Here, using the angle between force F and the displacement d, which is 180 degrees, and we obtain F times d times cosine 180 degrees. And since cosine 180 degrees is just minus 1, and the result is minus F times d. Using the formula of F that we have found in part A, we can write minus m times g times h over d times d. Here, these are cancelled. Then finally get minus m times g times h. Now, we can substitute the numerical figures into this equation to get minus 50 kilograms times 9.8 meters per second squared times 2. As a result, the work done by force F is negative 980 joules. Finally, the work done by the gravitational force is m times g dot d. It is easy to show that from this configuration, the angle between the gravitational force and the displacement vector is 90 degrees minus theta. So this formula turns out to be m times g times d times cosine 90 degrees minus theta. Also, remembering that cosine 90 degrees minus theta is sine theta, we get the formula as m times g times d times sine theta. Instead of sine theta, we can write h over d. Here these are cancelled and we finally obtain m times g times h. Now put the numerical values into this equation as 50 kilograms times 9.8 meters per second squared times 2. If you calculate, you will find the work done by the gravitational force as 980 joules. Okay, let's solve part C. In this problem, since there is no acceleration of the motion of the box, the net force acting on the box is 0. So is the total work done. This can be checked using the results in part B. The total work done by the net force is the sum of the works done by the normal force, applied force F, and the gravitational force m times g. Inserting the results into this equation, we get 0 minus m times g times h plus m times g times h. So, the total work is just 0 as we have claimed. Anyway, we have answered all the questions in this problem. Thank you for your listening and see you in the next video.